Okay, so why did I have you figure out how to do all those calculations for different concentrations? Well, we are going to talk about what are called colligative properties, and these are actually really applicable to everyday life. Okay, colligative properties are things that change based on the amount of solute you have dissolved, so your quantity of stuff dissolved. So, for example, salt on the roads in the winter, actually it changes the melting point of ice. It lowers it from 0 degrees Celsius. So the more salt you have dissolved, the lower the melting point. And that actually affects the road so that it's liquid instead of solid ice. Also, antifreeze in your car, it changes the melting and boiling point of water to make it so that your engine doesn't get too hot. So these are both examples of colligative properties, and I'm going to show you how you can actually calculate how to change a melting point or boiling point, or there's other properties too that you can change based on how much stuff you dissolve. So colligative properties are any property that depends on only the amount of solute particles in solution. So it's something that only is affected by how much stuff you dissolve. That's it. Okay. The four that we're going to talk about are vapor pressure, freezing point, boiling point, and osmotic pressure. Vapor pressure would mean the amount of gas, right, in a closed container. If you have a liquid in there, the amount of vapor pressure in the top part, it actually decreases as you have more stuff dissolved. We have freezing points also actually decrease. It's called freezing point depression. That's how the salt on the roads works. Boiling point elevation, so we raise the boiling point, and osmotic pressure also goes up. So these two increase with more solute and these two decrease with more solute. So I'm going to start with vapor pressure lowering here. So when a solid solute is dissolved, the vapor pressure will decrease. Now remember, vapor pressure is the amount of gas. So if vapor pressure is decreasing, that would mean I have less gas. Okay, so this is my picture over here. If you just have a pure solvent, nothing dissolved in it, this is the amount of vapor pressure, for example. But if you dissolve some stuff in it, actually less of it is gas and more of it will go into the solution. So you have a lower vapor pressure, and it does depend on the concentration of the solute. So there's a calculation for this. It's called Raoult's law. And it is that the partial pressure of a solvent for a mixture decreases by the mole fraction. So the reason we were doing mole fractions is because the partial pressure changes based on how much stuff you have dissolved. Okay, so the new partial pressure, we'll call it partial pressure or P1 or I or whatever it is, whatever your stuff is, your new partial pressure after you dissolve stuff equals the mole fraction of your solvent times whatever the pure solute dissolved partial pressure was. So this is a little not symbol. It's a little zero, like superscript. It means pure. That's your solvent without stuff dissolved. So that times the mole fraction gives you your new partial pressure, which should be lower than your original partial pressure. Okay, so example number 8 says, what is the vapor pressure of 40 grams of benzene, which has a pure vapor pressure of 86 millimeters of mercury at 25 degrees Celsius, if 10 grams of naphthalene, a non-volatile solid, that just means it doesn't turn into gas, is added. Okay, that means this is a solid or liquid thing that is added. Okay, so I'm going to pull out my numbers here. I've got 40 grams of benzene. I have 86 millimeters of mercury and 25 degrees Celsius if I need that, and 10 grams of naphthalene. So this might seem like a lot, but let's kind of break it down. I know it's a lot of words. Okay, so we've got, I'm just going to write again what I have. So I have 40 grams of C6H6. That's my solvent, right? Has a pure vapor pressure. So P naught of C6H6 is 86.0 millimeters of mercury. I don't actually need that temperature. I'm just telling you that the temperature is not changing. If I'm adding 10 grams of C10H8, okay? So this is my solute. This is my solvent. Okay, I know I'm going to need Raoult's law because I'm looking at changing the vapor pressure. Okay, so the law is P of my C6H6 equals XI, or X, I'm going to put the stuff down here, of my C6H6 times the original pressure of my C6H6. Now you'll notice here, this is not the mole fraction of the solute. It's actually the mole fraction of the solvent. That's what I'm changing a little bit here. So these all match. They should all be of the same thing. Okay, we're just kind of changing how much of this benzene per the whole solution there is. So I have this, I have neither of these. I'm actually trying to find this. This is my goal. So I need to find the mole fraction before I can plug it in. So if I want the mole fraction of C6H6, that would be the moles of C6H6 over my total moles. Okay, so now I just need to figure out how many moles of stuff I have. So I'm going to convert both of my amounts of stuff to moles. So I have 40 grams of C6H6 over 1. Its molar mass is 78 grams per mole. So that one, so I have 51282 moles of that. And then my other one, I'll do up here, I've got 10 grams of C10H8. Its molar mass is 128 grams per mole, and that is 0.078125 moles. Okay, so adding these together will give me my total moles. So that's going to go down here where my total moles is, and my partial is 0.51288. So I would do 82 over my total. So whatever those are added together, 0.59095. That is my X. Okay, so now I can plug that in. This, which is number I didn't write down, whatever that equals goes there. And this goes right here. So my pressure, erase that arrow. So my pressure, my new partial pressure is, again, that number I didn't write down, times 86 millimeters of mercury. So my new pressure is 74.6 millimeters of mercury. Now, again, does that make sense? Well, remember, when we start dissolving stuff, the vapor pressure should decrease, it goes down. And so it went from 86 to 74.6, so that makes sense. It went down just a little bit, nothing too crazy because it's based on the partial pressure of benzene.